understanding what that means, this means no IP, okay? No internet protocol. So here's kind of a rough outline. My experience with this talk is that I never get to the end, so when we're out of time, just tell me and we'll stop, okay? So I'll give a little bit of background. The XIA, somewhat similar to IP, is actually based on some core principles, which I will explain and motivate early on. And then I'll basically talk about the architecture in a bit more detail, and also talk about what it took to actually build one of these things, okay, so that we can actually run applications over it, which is obviously something that we want to be able to do. So, just to give a little bit of background for those of you who are not familiar with this, but I'd say about 8 or so years ago, so some people in the research community, in the networking research community, observed that a lot of the research that was being done was really highly constrained by the fact that it had to run on the internet. And the internet, defines and a lot of things, and there's a lot of things you can't change. And as a result, the research became highly constrained. And so National Science Foundation decided to basically start a program very specifically to look beyond IP, beyond the current internet. Okay? So this was defined as a multi-year, multi-phase, long-term effort. So what turns out that we're in the second phase of this. I'm not going to bore you with the details. You can go online and read about that. And as part of that second phase, there were basically 4 projects that were funded, and the project that I'm going to talk to you about is one of those. There's 3 others that are listed here, but I'm going to get back to those later, and I'll briefly mention them at that time. So the vision that we defined for XIA is actually both, I think, a mixture of obvious goals and not so obvious ones. So the first one is actually trustworthiness, I think, where generally speaking, trustworthy here basically means not just basic security, but also things like availability, something that's aware of privacy concerns and these types of things. So that's in fact not really a big surprise, I think, given the current state of the internet. The next 2 goals have to do with evolution. The first observation is that the current internet actually has been very successful in supporting new applications over time. In fact, it's been extremely successful. The original internet applications were all host-based, and so very few people in this room, maybe 2 people in this room, know this, like Telnet, FTP, these types of things. Today, it's all about services and content. Okay? Yet, this works over the current internet. The problem, however, is that these applications today are often very complicated because they're running over a host-based internet. And so the second kind of part of our vision is that we want to basically support long-term evolution of usage models. What we mean by that is that as new application paradigms evolve, we want to be able to support them very efficiently. Okay? The third part of the vision is long-term evolution of technology. And again, I think we need to give credit to the internet in the sense that it actually has been very successful in running over different types of link layer technologies. The original internet effectively ran over telephone lines. Okay, roughly speaking, that's correct. Today, there are very few telephone lines in the internet. In fact, the telephone system runs on top of the internet. So we have optical fiber, we have wireless, which is obviously of great interest to this group here and to me myself as well. And so basically, when we say here we want to support long-term technology evolution, we want to continue to do that, but on top of that, we want to be able to accommodate advances in things like computing and storage technologies. These things, because of the very simple forwarding model that is used in IP, it's been very difficult to actually leverage these new technologies in the internet today. Okay? So this is not just link layer technologies, but the whole technology spectrum that we care about. And then the third part is actually a very interesting challenge. This was more or less suggested to us by NSF, but turns out to be a very important and interesting part of our project, is that fundamentally the internet is not just a technical artifact. The internet is part of the economy, it is part of people's social lives, and it's basically an integral part of society. And we basically want to make sure that whatever piece of technology we define can also play that role. Okay? And so, for example, you want to make sure that ISPs can make money on this. Otherwise, they're not going to deploy the technology, just to be kind of blunt about it. And so I'll touch briefly on this because it turns out this actually drives a lot of our decisions, strangely enough. Yes?
Do you define the forwarding as something that you're going to allow to be changed? So for example, right now, almost everything in the internet is and multi-asset broadcast is sort of we're pushed to the side. So does this allow for them, or does it offer incentives for doing that, which is why we don't have them now?
So the answer is we have looked at this, but I think we can support that much better. But that's actually maybe a question to ask at the end again. Okay? So we have more context then to have for discussion. Before I actually go on, please ask questions as we move along, because I think this is a little bit off the wall, and so I think making this interactive, I think is useful. So one of if you look at my previous slide here, two things have to do with evolution in the future. Okay? So let's start by first agreeing that predicting the future is very hard. And so to illustrate that, I'm actually going to use the three other projects that are part of the Future Internet Architecture program to make that point. The first, one other project in the program is something called Named Data Networking, which is better known as CCN, which is basically Van Jacobson's project. And, well, it's not his personally, but he's the driving force behind it out of Xerox PARC. And so they firmly believe that content rules. Okay, and so it's actually, to be honest, a little bit hard to disagree with that. If you talk to the people at WinLab at Rutgers, they have a project called Mobility First, and they think that mobile users who are wirelessly connected, are the future. And again, I don't think this crowd is going to disagree with this, right? And actually, I'm a big fan of this one as well. And then we have some colleagues at UPenn who have a project called Nebula, which basically argues that it's all about cloud computing. I have a lot of colleagues working on cloud computing, and it's hard to argue that cloud computing isn't important, right? So now the question is, if you have to build a network for the future, what are you going to focus on? The content, mobility, cloud computing, trustworthiness and evolution. I mean, what is it going to be, right? So the argument is that asking us to choose makes no sense whatsoever because we're going to get it wrong. And so what we really would like to develop is an architecture that can, over time, evolve and change itself. So you don't have to come up with, IP version 23, when the next thing kind of comes out. We'd like to be able to say, hey, we just, change something. The architecture stays the same, and we just evolve the architecture. So to illustrate how XIA works, I'm just going to use a very simple example. Okay, and this is actually, I part use this example because you don't actually need to know all about networking to understand the example. So this is how today's internet works. I'm going to use Jane here, who has a PDA or a cell phone, wants to retrieve a document. So the way this works today is that you have a lot of preliminaries, but then fundamentally at some point, Jane's cell phone is going to send a packet to a server that has as a source address, an IP address that identifies her cell phone, and as a destination address, it identifies the server. Okay? These are two very specific machines. Then that packet basically asks the network, please deliver this packet to this server, right? And then this packet gets delivered to the server. The server ends up returning the content using some kind of a protocol like TCP, okay? So when you look at this, the irony is I've been teaching this approach to networking for 15 plus years, right? So for a long time I actually believed this was obviously the only sensible way that you could build a network. But if you actually look at this a little bit more closely, you discover that this is a little bit off. And the reason is that there's kind of a disconnect here between what Jane wants and what her cell phone asks the network to do. Jane wants a document. She doesn't care about servers. She doesn't even know what a server is, okay? But the packet that goes into the network specifies specifically, please deliver this packet to the server. Now, we all know that 90% of the time this is kind of okay, it works out okay. But there's certainly a couple of cases where this mismatch between what Jane wants and what the network is asked to do hurts you. The first one, obvious one, is what happens if the server fails, okay? So that's an obvious one. Another one is that a lot of the content that people retrieve is popular and is actually highly replicated. Okay? The problem is that since the network can't easily find out what Jane wants, the network can't make use of these local copies that might be available, right? Because it's being asked to deliver a packet to the server. Okay? Now we all know that there are things like proxies that may be transparent or not transparent that can help in dealing with the second problem, but these things are pretty brittle, okay? And in some sense they involve peeking into the packet, they involve security, they raise security concerns, and so on. So instead what we propose in XIA is something a little bit different. So we still have the same PDA here. The packet that is sent into the network has, however, a different structure. The source address is still the IP address or the XIP address of the PDA, because ultimately that's where we want the content to appear. We don't want the content to appear on Jane's desktop, it has to appear on her cell phone. But the destination address that is specified is actually an identifier for the content that Jane wants. So what we've effectively done is we've kind of lined up Jane's intent with the intent that is expressed in the packet. So effectively the application directly tells the network what it really wants to achieve, rather than just kind of having a couple of levels of indirection there. And so the idea now is that what that packet effectively does is it tells the network, this is the content I want. I don't care where you get it, okay? But this is what I want. Now, there's a lot of issues here that I will talk about later in terms of how you make this work, but I do want to raise one particular challenge here, which is that if I'm your average user and I send a packet in the network that says, get me this content from anywhere you want, I might get a little bit of worried whether that content is correct, right? I mean, I think there's a valid reason. Now, there's a little bit of a caveat here that in many cases, people end up getting content from places where they don't really know where it's coming from in the first place, but today people don't worry about it because they don't know that it's transparent, right? But here, certainly there would be a concern. So XIA has this concept of something called intrinsic security, which, as I will more precisely define later, but it roughly means that it's easy for Jane's PDA to basically verify that the operation was executed correctly. In this particular case, intrinsic security simply means that the content identifier is effectively a hash of the content itself. So you take the content, which is supposed to be static content, it's a string of bits, right? You make a hash over that, that's the identifier. Okay, it's not a new idea, it's been around for a long time, but effectively what it means is that the moment Jane's PDA has the correct content identifier, it can very easily verify the correctness of the bits of the bits it receives once they arrive. And so it turns out we actually extend that concept, and I'll briefly mention this later.
I have a question.
So, yes?
Yeah, so how does Jane know the hash of the content is in packet content?
Okay, now this is the slide. So, you know, that's always the question I get, which is why I added the slide. So this slide, basically, the bottom here is the same as what I had in the previous picture. So basically, a packet is sent to the network that identifies as a destination content ID, and then basically the network can retrieve it from anywhere, it comes back, you calculate the hash, and you correct and compare it with the content identifier. But then the question is, where does this magic content identifier come from? This is like 160 random bits for all practical purposes. Nobody will memorize these for sure. So it turns out that the answer that this approach that we use for this is not unlike what's happened today. And we basically use the term trust management for this, and you'll see that on some of my slides. Fundamentally, at some point, Jane is going to need to look at a name that she recognizes and says, this is really what I want. Right? This is, I can read it, and in my judgment, this is the document that I want. And then she needs to go to a trusted source that will map that content, that name, that human readable name, onto a content identifier. Okay, this is a very traditional problem in security. You can't avoid it. Okay, it's just part of life. And so we call that trust management. Now, effectively, the way we look at this, the thing that will translate the user, the human readable name into a content identifier, effectively delivers a service to the user. Okay, so how does Jane's PDA contact the service? Well, it uses a service identifier, which is shown up here. So rather than sending a packet to content, which seems inappropriate, or a packet to a host, which also is inappropriate, the packet is sent to a service, which effectively, with a request that says, hey, I have a content name here, can you give me the content identifier? And then the service will respond and say, look, hey, here's the content ID, and now I can go through some attention. On one hand, you can argue that I've just pushed the problem further down the road. On the other hand, I don't think I really have, because without trust management, you can't build a network, right? I mean, and so the key issue here is that you need to make this trust management explicit, and also do appropriate research that users know how to use the problem. Okay, there's a part of the project that's looking at that. Yes.
Is a service ID or DNS?
So that's a very good idea. So what is the service, right? Mm-hmm. So let me give you a couple of examples. First of all, yes, DNS would be an example of a trust management service in the sense that it maps a human-readable host name into an IP address, which is not quite cryptographic, but is certainly hard to remember. Okay? So DNS would be an example. Another example would be a plain old web server. Your human-readable name could be URL. Right? And people trust content based on URLs all the time today, for better or for worse. And so, presumably, if you have a URL that says CNN.com, you would trust CNN.com to probably map this to a content identifier. In other cases, but I envision if you look further down the road, this could be your friend. For example, you could imagine that you're on Facebook, you have befriended somebody, hopefully, and they want to point you at a web page. And hey, by the way, here's the content identifier for this web page. It worked for me, you trust your friend, you use the content identifier directly, and you don't have to go through a whole separate lookup because you trust the source of the content identifier. This is all what it boils down to. Does the user trust the content identifier? Okay. And so this is a project that's only a year and a half old. Obviously, we have a way to go here, but that's kind of the high-level vision. So we have diverse communicating entities. We have intrinsic security, and then we have this whole trust management, which I will not talk about much today, but we may have a chance to talk about it later today.
Yeah, well, but this requires, right, third-party trust management or trust authority or something like that.
Well, that's an option, but we, to a large extent, would like to avoid those.
Because if you don't do that, then it can be played. Especially the URL can be played.
Can be replayed, is that what
Can
you
be
said?
played, can be attacked.
Yes, and so let's maybe talk more about that later. So I briefly want to kind of highlight these principles and then move on. The first one, evolvable set of principles. The reason why I want to highlight this is that there are 2 points to this actually. The first point is that rather than forcing everybody to send packets to hosts, we're allowing you to send packets to different things. Like I mentioned, services, content, and hosts. However, the more important thing is that I am willing to bet that 10 years from now, there's going to be something else people will want to send packets to. I don't know what it is, okay? But the good news is I don't actually have to worry about that because we will develop an architecture that allows us to add this thing 10 years down the road without having to reinvent a new version of IP. Okay, so that's the evolvable part, yes?
I'm just curious, did you ever consider either a different model, like not using packet switch networks? Like, I know this is kind of silly, but it's the inherent assumption in all this is that we're going to stick with the similar packet switch methodology that we're using.
Yes, we spent about 5 minutes on that. And I'm actually not entirely kidding. We actually, at some point in the brainstorming meetings we had, I did say, you know, can we kind of make sure we go through our assumptions here about, you know, like fairly fundamental ones like that. And but the fact of the matter is, coming up with anything else, it effectively ends up being something like circuit switching, and I'm not sure we really want to go there, right? And now it turns out that and unfortunately I don't have time to talk about this, but maybe later we have a little bit of chance to chat about this. One of the control planes we're exploring actually has more of a circuit switch flavor, but it's implemented on top of this, okay? And so we can talk about that later. So the second idea is intrinsic security. I'll actually talk more about this later, but it is basically the notion that you can easily verify the correctness of communication operation. This does not implement all security. It's a very narrow aspect of security, namely certain properties of the communication operation can be verified. Okay? And it can do that without actually relying on third parties. Okay? Which is important because that's where the attacks happen, right? So this does not solve everything. It's a very narrow way of bootstrapping our security mechanisms. oops, okay, this is really late. The other thing I actually really want to now get back to, this actually gets to your question. It turns out there's a number of other principles. We have a notion of a narrow waist. We like that in the current internet, so we're sticking with this. Okay? Except our narrow waist is a little bit thicker. But our argument is that technology today is very different from that 30 to 40 years ago, so we can afford to have a slightly thicker narrow waist. Okay? In fact, you can in fact argue that as you add new principal types over time, you're going to make your waist a little bit thicker, but if the technology can handle it, that's okay. Okay? There's a narrow waist for trust management, which I'd rather discuss offline. And then we have this other thing where all other network functions are explicit. All other network functions are explicit services. It turns out that's actually also what the current internet does. So the example I always give is the DNS example. DNS is essential to the current internet, but it's a service, right? It's not part of the architecture. Actually, I have considered putting packet switching on the slide, because it turns out that the first, the last, and packet switching are all ideas that we borrow from the current internet. Okay. And I can't think of a good alternative. So now let me explain the name. So the expressive internet architecture basically means that every communication operation allows the application to express its intent by picking the right communication. I actually briefly, even though this is a little bit philosophical, briefly want to compare this approach to some other approaches out there. One approach that has been proposed for future internet architecture is to rely heavily on virtualization. So the idea is that I have a common hardware infrastructure. I use virtual machine technology, which is obviously very well understood at this point, which allows me to bootstrap effectively multiple network architectures on top of the same hardware. And you can say, hey, I want to do content-centric networking. Let's create a virtual network for that. Service-centric networking. Let's create a virtual architecture for that. So this is another approach. I'm not going to say this is a bad idea. There's other people exploring this. The particular challenge that exists with that approach is that if you want to have your content-centric networking endpoints talk to your service-centric networking endpoints, that kind of becomes a little bit hairy. Okay? And that's really the primary challenge, I think, one of the challenges you need to address there. Am I going to say this is a bad idea? No. Okay, but let's have how other people are exploring that. The other one is to say, look, hosts are no longer popular. Why don't we replace hosts as principal types? So, for example, if you do a pure content-centric networking approach, you're effectively saying all packets are being sent to content. Okay? And so now, again, I'm not going to say this is a bad idea, but the obvious drawback that we have is that you now have to, if you actually do want to talk to a host, you have to kind of pretend it's content or something like that. So it turns out that you've kind of potentially moved the problem somewhere else, right? And so these are alternatives. It turns out that there are other projects that I mentioned earlier who are exploring these. And we're just exploring a different part of the design space, and at some point we can compare notes. Okay, so that's kind of how this lines up. But I mean, we are distinctly taking a different approach. That's fundamentally different, I believe. I'm actually not going to talk about that. I want to give you a little bit of some confidence here that this is not completely off the wall. It turns out that our protocol stack doesn't look all that different from today's protocol stack. We have the red stuff, which is effectively replaces IP. We run services on top of that, and it includes things like transport services, which we look at as a service. We have applications, they sit on top of that, so there's some rough layering there. Distinction between applications and services is obviously fuzzy, we all know that. We also have users. And then we also worry, it turns out that APIs are very important interfaces between things, right? And so we worry a lot about those. And interfaces are important, for example, if ISPs want to make money, how they can talk to their peers is very important, okay? And so that's kind of where these interfaces come in. Interfaces also come in when you deal with users and applications. You know, you can put all the features in the network that you want, but ultimately an application has to be able to use them. And then obviously there's the trustworthy network operations. You need things like routing and all that kinds of good stuff, right? Yes?
So I noticed hardware is missing from here. There are probably some fundamental things you'll need from the hardware that are different than we have now. Like cams will maybe go away. Or I don't know, maybe some other.
Yeah, that's a good point. This is another priority for the project.
Oh, really?
Okay, so we have some people in the group who are working in that space, but this is not something we worry about too much. Actually, arguably, the industry is going to do a much better job at this thing. And it's maybe a mistake, but we
But
can.
are there some fundamental hardware elements you'll think you'll need, or
Nothing so far.
About principle matters. Principle, you might think of elements, but what principle should we change in the hardware to support this?
In terms of design principles.
Right. Oh.
Well, maybe I can explain the architecture a little bit first, and then we can talk about that. Okay. So I'm just kind of want to emphasize this. This is more of a way of introducing the people in the project. There are 11 principal investigators. You know, project is probably about 25 people. No, that must be more than that. It must be closer to 35. And so the biggest group is obviously the core networking group, because this is a networking project. Then, you know, most of the people are at Carnegie Mellon, but we have also John Byers at the BU, and I think Yakela at Wisconsin has involved their students, of course. Policy and economics plays a big role here. We have Martin Serbu and John Pita involved. So they are people in the engineering and public policy department at Carnegie Mellon, so they're very good. And so they're looking at things like economic incentives, business models, deployment models, and that kind of stuff. Users are important, and this has for me been one of the most interesting parts of the system. We're working with Sarah Kiesler, who is in the Human Computer Interfaces Institute, and who specifically specializes in how trusting technology affects users' use of that technology. And so this has actually been very useful, very educational for me personally, actually. Unfortunately, I'm not going to have a lot of time. I only have one slide that touches on this, actually. And then we're working in the area of trust management, and also network operations like routing management. Trust management is what we were just talking about. How do you map human-readable names into cryptographic identifiers? There are a lot of interactions between these things, which what XIA is all about. Okay, so the first thing I want to... Excuse me?
How many notions of trust?
I'm sure I know how to do
So there is direct trust based on experience I have with you. There is reputation trust. There is
So
physical
So I'm going to give a short answer, and then maybe we can elaborate later. One of the things that we want to do is build some kind of we call it narrow waist, because we were called it narrow waist at the time, but it is a notion that in different contexts, different models of trust are appropriate. And so you need to support those. But more importantly, if we can find ways of having these things kind of cooperate in a way, we really come out ahead. So you can say, hey, reputation says that this looks okay, and then maybe there's something else that contributes a little bit. You can combine these somehow, and then if you can convey it to the user, you're in really good shape. So there's kind of this vague notion attached to direction. So this project was actually very unique in a way of how we get it started, in the sense that we had basically a team of 11 faculty writing a proposal that includes a draft of an architecture. But what everybody in this room knows or should know is that ultimately it's the students who do the bulk of the research. So there's kind of like, how do you go from a bunch of faculty owning an idea to a bunch of students owning the idea? So basically what we did was we recruited 7 students, okay, for the core networking team, and said, look, we have 15 pages of text here. You think you can actually make this work? Not only that, you think you can improve on this, okay? And so, and we kind of went and started doing our teaching and our writing of reports and our whatever, right? All the other stuff we do, our travel. And so they went actually off and turned this kind of very vague ideas into a real system, is the way I would put it. And so to a large extent, what I'm going to talk about in whatever minutes I have left, is really about what they did with this. So I want to talk very briefly about evolvability, because this is really the idea that I think is probably the least explored. So let me first be clear by saying that I have a lot of respect for the internet, okay? So the internet is traditionally represented as a protocol stack that can be modeled as a narrow waist. A lot of different applications, a lot of multiplayer technologies, there's one IP. Okay? The internet has been exceptionally successful in allowing evolution here and evolution here. Evolution here is zero. Okay, we're flat. Okay? And so what we really would like to do is we would like to keep this and this, and that's also one of the reasons why we stuck with the narrow waist idea. But we also want to allow evolution here, and that's where this multiple principle type idea is like. By adding new principal types over time, you can effectively evolve the network. That's at least the hypothesis that we have. So here are the principal types very quickly. We have hosts. I think you all know what they are. They identify a specific piece of hardware that you want to talk to. So it identifies who you talk to. So it's kind of like an IP address. You have services. The services basically identifies what you want to have done. Right? I want to do a lookup using Google, or I want to draw. I want to get news from CNN or whatever. Right? It's almost, you can think of it as a web server that does something specific for you. The key difference here between these two is that here there's only one. Guaranteed, there should be only one. This can be replicated. Okay? The third thing is content. Content basically means a fixed string of bits. This is static content, not dynamic content. Dynamic content is a service. It's generated on the fly for you specifically. This is static content, so it basically defines what the bit string looks like. Okay? And so the nice thing about this is that you can massively replicate static content. Do that today. Okay? And so all three of these service types have something different to them. They are not the same thing where it's just humans who look at it differently. The network can handle them differently. That's the thing. And then there's kind of like the dirty little secret. We also actually have network identifiers, which we call ADs for autonomous domains. And we simply need this for scoping, for scalability, hierarchy, for all the types of things that work well in today's internet as well. So we don't throw that out this as well. We can have very fascinating discussions about what the next principal type should be. Okay? And let's not have this now, we can have that later. Someone was asking about multicast, I actually forgot already. It was. That's my favorite, actually. It turns out to be tricky because multicast has very different flavors. So let me just briefly illustrate this. So I have a network here, I have been PA here. She wants to retrieve a piece of static content. One way of doing that is to say, hey, I'm sending a packet to the host, just like you would today. And then the semantics with respect to the network are that you're telling the network talk to that host. There's no choice for the network, no optimization criteria. This is literally what you want to happen, right? No matter where that host is. Static content can also be retrieved using service identifiers. And so in that particular case, you get the yellow arrows. And now there's some opportunity inside the network to replicate that service. Like most large websites are replicated already, right? And so the network can pick the one that's the closest. Today, this is done using DNS tricks, if you want. So here you can have a network here. And then finally, if it's static content, you can basically use the red content identifiers. And in this particular case, they can actually do massive replication. Okay? Now, yeah.
This reminds me of peer-to-peer network.
Actually, some other people have pointed this out, except that this is peer-to-peer network that's pushed into the network layer, right? We're at a lower layer than today's peer-to-peer. Some of these ideas are obviously not exactly caching. So now, here's my question for you. If you are a user, which one would you want? Would you want to do the blue stuff, the yellow stuff, or the red stuff? Or the host stuff, the content stuff, or the service? Well, what do you think is going to be the best for you?
Best me.
Yeah. Best? Well, you're the user.
Because first time,
Whatever Firefox implements.
Whatever Firefox implements. Now that is a very interesting and lengthy discussion that we should have, actually.
supposed to direct.
No, actually, seriously, people say fast, robust.
Fast recovery.
Fast,
Robust.
robust. So I would argue that for fast and robust, red is clearly better. So that means you all want red?
No.
No, okay, you don't want red. What do you want?
I mean, Can you verify the context providers inside?
Yeah, you can. There's the intrinsic security. So security is not an issue here.
Users aren't going to be interacting with it.
So they actually will, and but this we're going to have to take this offline. So it turns out that the red stuff is obviously what we intend people to use, but it turns out that there's another little thing here. Just because you ask the question, can you verify the content, where you can convince the user of that is a different matter. Okay? But more important, there is actually a privacy issue. If you blast a packet in the internet and you get the content identifier, you know, it's pretty easy for everybody in the world to see exactly what you're looking for. You know, some users are a little bit uneasy about that. And so, well, a lot of people don't understand that they have an issue. So a lot of people, so what I should say is for some content, people care a lot about this. For other content. And so it turns out that one of the things that's really happening here is that there's a trade-off here between these two types. Okay? That involves control and efficiency, and also trust and privacy issues. There's an issue of how you have users deal with this. There's also, but there's also another issue that I want to point out, which is that in the current internet, that trade-off doesn't exist. All the control lies with the network. Here, there's potentially some control that is actually being given to the end users, right? And the point is that the end user choices in picking principal type is going to affect the efficiency of the network. So the service providers actually care what the users pick. Well, the network providers actually care what the users pick. So there's this interesting balance here between user control and network control that is being changed, okay? And that's why people like Marvin and John Beha, Marvin Server, that is a John Beha. Okay? I'm not, actually, how much time do we have? So now, I've been talking about evolvability being the best thing since sliced bread. And I'm actually stunned that nobody has asked me how I'm going to make this work. So now let me try to explain how we plan to make this work. So suppose that we have an XIA network today that supports hosts, and I want to introduce content as the next principal type. So the simplest way of doing that is to have what is sometimes referred to as a flag day, which is that everybody switches off all their routers and all their computers on a certain day at a certain time. They upgrade them to support content, and then 5 minutes later they're switching back on, and everything works again, right? So I see some people smile, which is actually good. So obviously this isn't going to work. No flag days, okay? So what that really means is that very fundamentally you have a chicken and egg problem, and arguably, I don't think that's really the biggest problem with IPv6, but it's a little bit of a problem. If I'm an application developer, why would I use content identifiers if it's not supported by the network? And if I'm the network provider, why would I support them if there are no applications supporting them, right? And given the big businesses involved here and the effort in doing this is a big deal. So we're actually going to do something really bizarre. This is your normal packet that we would like you to send. We would like you to send a packet to a content identifier, and then the source address is likely to be a host address still. Okay. Now, what happens if a router receives this content, this packet, and it looks at the content identifier and says, CIE, never heard of it, no idea what it is. You know, what does he do? He's going to throw the packet away, right? So that's a bad idea. It turns out the problem is actually worse than that. There's general consensus that given the current state of technology, content will never be universally routed. There will never be a single router that has forwarding table that has pointers to all content in the world. That is just not scale of those defenses. So even if the router recognizes the CID as a type, as a principle, it may not recognize the others. Okay. So what we basically had originally thought of is that we have a notion of a fallback address. So your address effectively has two parts. It has a content identifier, which is the intent. And in case a router gets confused by this, there is a good old-fashioned fallback, which is a more traditional, well-established type of identifier, which will be used by the router if it doesn't recognize the first one. Okay, so every router will first look at this. If it doesn't recognize it, it will look at this, and presumably this will bring it closer to wherever.
So you don't allow secondary transmission or requests.
That's an alternative. It's up to the user, right? So if a user wants to say,
But if I can go to the server, I don't recognize it, but then I know others that may have it, and I forward it there.
right, and so, but we decided that force this as the only solution is inefficient. Right. So just to clarify, the solution would be to only allow CIDs. If packets to CIDs get dropped by a router on the way, then the request will time out, and the source will resend using the host ID, right? So if this looks like a really bizarre way of going about this is not strange at all. Content identifier could identify a web page, and this would be the host address of the server that has it, the web server that has it. Right? One of the things that I, just for future reference, when I talk about addresses throughout this talk, I mean the whole red thing. I mean the combination of the content identifier and the host identifier. Same thing, you do a name lookup on DNS or wherever, it's going to return the whole thing, the whole red thing, intent and fallback. Okay, so
Because, so you don't, so in peer-to-peer networks, the reason we were very successful to find content fast in a single way, because we allowed secondary and ternary distributions among the nodes. So if I don't find it, I send to others, and there are very efficient protocols to do that.
yes, but I think
Including things that they resemble network coding maps.
yeah, no, I understand this, but this has to run. This runs at a much lower layer in the stack. Okay? So this needs to run at hardware rates. In fact, you'd like forwarding at IP is somewhat predictable in this quickly it goes. So, I mean, it's a design decision, and obviously we can't prove that this is the right one.
But the method I described doesn't make the waste efficient. It doesn't affect the waste. So,
No, that's exactly right. It keeps
It affects the
now.
time.
Yes, you're 100% right. We ended up making the waste a little bit bigger. So it turns out that if you actually look at address requirements, there are a lot more than that. There's a fallback. It turns out you really also need to have scoping for scalability. Okay, I hope you're all aware of this. Current IP addresses are really a network identifier, a host identifier. Without this, the whole network work. We need the same thing. So that's why we identify these autonomous domains as another type. And then there's a notion of defining that one, which I'm going to explain a little bit later. But then basically what we discovered was that giving a project and handing it to students, things become dangerous. So students basically looked at all this and said, this fallback idea, this is kind of lousy. What we're going to do instead is we're going to use directed acyclic graphs as our addresses. Okay? So the idea is that the nodes in the graph are identifiers of the variety that I've discussed so far, and then you just build a DAG. And as the packet progresses through the network, we're effectively walking the DAG. And so another way to almost look at this is that the DAG is a data structure that the source provides to the network to help the network find what you're looking for. Okay? Not quite as flexible as what you were describing, but it's getting there.
it's going in that direction.
So I'm curious, and I'm sure you'll get there, how routing protocols are going to have to evolve. So now you're going to have to be flooding content identifiers, or there's going to be just caching of content identifiers. Like, how's that going to work?
We'll get to that.
Yeah, that's
I just keep saying it.
I know,
We're
yeah,
out of
no.
line here, right?
the paper's out there, basically.
Oh yeah, the papers is out there. It doesn't answer all these questions though.
Oh, it does.
So anyway, let me first give you a simple example. This is the example that I've discussed so far. This would be the address. This is a dummy source. The solid arrow is the high priority arrow. So it basically says, what I want is really this content identifier. Okay? But hey, if you don't know what that is, I have a dash arrow here, and then just take you to that host. Okay? And so it just captures the notion of a fallback address. So just to stretch this a little bit, we can also do scoping. The picture up there is in fact a DAG. So I have a dummy node, then I point at an AD, which would be like a tier 1 AD, this would be a regional AD, and then there's a host within that AD.
Who supports the DAG?
Who supports the DAG?
And
Name
so-
service supports the DAG.
And its evolution, right? Because it's very dynamic.
Yes, but the evolution is on a long time scale, right?
Yeah.
Years.
It changes.
It changes over time.
So who supports that? Service.
Yes, so I mean the name service will return the DAG. Right. So the point is that in this case the host, the owner of the host will define the DAG that is used to reach it. Okay, and we'll publish that with the name service. Okay, which makes sense, right? So they obviously have a vested interest in being reachable, so presumably there'll be a tag that makes sense. And then we can do things like iterative refinement, which is that I really want a CIP, which I know is actually exists at this AE, because it's published by this organization. I really want to, this host I know has it, because that's a web server, and there's a scope address for the web server here. But anybody along the way that has a cached copy of this should be welcome as well. So that's a good sign. So now it turns out that there's a huge number of questions here that we're starting to look at, right? How expensive is this? Hey, we actually solved that one, so I'll have some slides of this later. How big will addresses be? Personally, I think they're small. How do ISPs verify policy compliance? Well, that's actually interesting. And I'll almost say the moment you tell me what the policy is, I'll tell you how hard it is to do this. It turns out that that's actually the harder part. What's the policy of the ISP? But we've started to look at this. If you actually have very simple policy requirements, like something along the lines of the basic GP, it turns out this is pretty easy. But clearly in the general case, this is hard. Specifically, we need to be concerned about people attacking the network or providing challenging acts. Which is the next one. Can it be deployed incrementally? I'm going to skip that part. I can discuss this with you offline. It turns out that we found a really cute way of actually using DAGs to have backwards evolvability in terms of running XIA over IP, which turns out to be kind of cute. And so that was really not one of the goals of the project. It kind of fell out automatically out of the DAG. A little bit about intrinsic security.
Is the DAG information provided centrally or is it distributed?
Oh, no, it's distributed.
The DAG information.
What do you mean by DAG?
I ask a comment and somebody has to give me the path of the DAG that I have to follow. Is that provided centrally or provided distributed?
So it's really distributed.
So who maintains, in other words, information about that?
So the destination, the organization that is responsible for the destination generates the DAG.
And isn't it DAG in every package?
It's a DAG in every package. So right now our addresses are on the bid side.
So big, right?
Yeah.
If you had like next step or next two steps, it would be much more.
Yeah. And but
Right.
Well, I was just going to say, but this is where the packet switch networking question sort of comes up, because ideally you would just want to throw a DAG out there and just get the flow back and not have to worry about a DAG for every packet.
So now you're getting into the types of questions that we're starting to look at. So it turns out that if you take your network DAG, it potentially has two elements to it. So the first one is this like discovery mode. The other one is the streaming mode. We actually have a notion of DAG rewriting or binding, where once you've gone through once you've done the first packet and you find a particular piece of hardware for a product, you can actually rewrite the DAG to make sure that you continue to talk that same piece of hardware. And so then you can potentially dramatically simplify the DAG because you no longer want to do these hardware. Have we solved this? No. Do we know this is possible? Yes. Do we look at it? Yes. But we haven't really done this. But there is kind of this thing that, yes, in fact, the DAG rewriting or binding is required. This is not optional. This is not a proposal. So if you're talking to the bank, you better talk to the same server about the same session. So intrinsic security. Actually, how long do we really have? So I can, 10 minutes.
It's okay, if you want more, we can have you more.
Well,
We run this very informal again.
Okay, so I'll shoot for 10 minutes and
But we start me.
okay, but once you all think because of hungry,
Good job.
so for intrinsic security, I briefly explained how it works with content with the calculating a hash of the content. For the host identifiers, we're relying on earlier work, which is a protocol called AIP for the calculating content. So effectively, what that means is the identifier is a hash of the public host. And this gives us certain accountability problems, which I'm not going to be getting going to accountability paper. I'll have someone to talk. And services right now use the same same identifier for that. The primary thing I really want you to take away from this slide, however, is that the nature of the intrinsic security properties that are guaranteed depends on the principal type. So if you use a content identifier, what you're basically being told is that the bit string is correct. Right? If the service identifier tells you that you're talking to the right service, and if the voice identifier it tells you that you're talking to the right piece of hardware. Right? Well, these are very different things. Right? Now, whether users will appreciate that is a different matter, but certainly from a technical perspective, knowing that you have the right bit string is a much stronger assurance than knowing that you're talking to the right piece of hardware. So that's kind of the thing here. So when you're looking at your trade-offs of getting the right content, the right XIA type, it's kind of part of the work. We don't fully, we're still actually working with this. This is a little bit. I have a somewhat elaborate example here that I'm probably not skip, but it basically illustrates the concept of blending. It also shows how you can design support mobile users, mobile services. Yeah? And it just simply means that you change the tag as you move around. I'm going to skip this because it's a little bit important. So now, I want to spend basically the remaining of time talking a little bit about how we build this thing, and about the group type. So the thing that's interesting is I've actually been able to talk about it in network architecture. I haven't shown you back in there. So
does the work involve any proof of properties, either by actual analysis or by proof of properties?
So I think the intrinsic security properties rely pretty much on the existing work. Right? But otherwise, the security properties, we don't have to specific classes. I think this has to happen.
For instance, you mentioned the problem of trade-off between performance of users and their perception of the trustworthiness of whatever they use. It's called in some service for quality trust.
Well, that is something we all about here. But this is not a formal, this is a study study. What? This is a study study. It's in front of users and say, hey, here are your options, and here's the cost, and here's the appropriate guidance.
It's very valuable.
Yes, that's what Sarah Kinsler does. I grew up on that. So the way to think about this is that the addresses are tags, and so we need to basically map this into a linear representation that fits in heading. The way we're doing this is I think pretty obvious. Your address effectively looks like an array of nodes, and then for each node, you have little store pointers to other elements of the array. You have like the edges of the graph. Right?
What's an idea how that the address coming to
So each, the CID, the content identifier is 160 bits. And so multiply by the number of nodes and add a couple of words. Okay. We can have a separate discussion that arguing that the network community is completely the same. So we fix the size packet for 19 all the nodes and we have a lot of forever. And we have to do that. I'm not going to solve that problem, but hopefully somebody will.
And some on the other hand, you cannot have an address that 1 million times the data. Well, it's not sufficient.
I'm not sure efficiency is a big concern.
Okay, because a guy from Germany came here again about 2 years ago and as I worked his huge addresses was pretty fine.
Right. So it turns out that
And they were huge actually.
like huger than ours.
Well, it depends on the number of nodes, but it's good.
Okay. So, but anyway, so we're effectively linearizing. So we have 3 nodes here, 1, 2, 3, and then for each node we identify the next entries in the array as the next node, right? And they're prioritized. So the first one is the and the second one is the So this is kind of what it looks like. So we now feel like this is real. Actually, the thing is that we have things like hop limits. Okay, so we like certain ideas of the internet. The other thing I want to point out is that there is a actually the name is confusing, but it basically identifies where you want the DAG link. So as you remember, there's a note, you traverse the DAG as you go through the network. There's a pointer in the header that says, this is where I meant the DAG. So let me give you an example to do this. Effectively, the way this works is that this is the last specific node. This is the yellow thing I had on the previous slide. So the source, that's the current last specific node to use. What this basically says that any router, what any router that receives this packet will do is it will look at the last specific node, go to that node, it will look at the first edge, the high priority edge, and see whether it knows how to get that. Like, if the answer is yes, it will do it. If not, it will fall back to the second node and see where it can do it. Okay. And we actually, in our current prototype, we allow up to 4 because I'm not clear you ever need that, but that's what the current prototype does. If you would actually reach ADS would update the port here. So from now on, you would basically be forced in this particular DAG to follow this particular path. Okay? So that you would effectively really progress through the DAG.
And are you chopping off addresses as you go along?
We actually leave them in the header. I guess you could drop them. We need a forwarding engine, the same way you have a forwarding engine in IP. This is our forwarding engine. Sorry, unfortunately I discovered that I didn't replace this slide by the first version. So I'm going to ask you to pretend for now that this part doesn't exist. Okay? So the way to think about this is that this particular block here will look at your destination DAG. It will look at the next current header pointer or current XIA pointer. It will determine its type. Then if it's an AD, it will has an AD forwarding block. If it's an HID, it has an HID forwarding block, etc. It turns out that for all current identifiers types, all these forwarding blocks effectively do a lookup in a flat forwarding table. So they kind of all do the same thing. Okay? But potentially you could imagine doing different things over time. Okay? If that lookup fails, you basically have a failure. You go back here and you look at the next node of the DAG, fallback node of the DAG. So that's kind of what this looks like. So a side effect here is that cost for lookup may be variable amount of time depending on how many options you look at. It turns out that we also have, before we actually do this, we actually also look at the source identifier. Because sometimes, based on the source identifier, you may want to do something special. The only case we have of this right now is actually for content. If the source identifier is content, it basically indicates that this is content, okay? And you may want to opportunistically cache this. So if you're a router that is able to cache things and may want to cache content, you would actually have this block to identify whether you want to opportunistically cache it. Okay? If you don't do that, you wouldn't have this specific. And then the final point I want to make is that we have two colors here. We have blue and white. White is effectively the logic for interpreting a DAG. And if you want to be pure and minimalistic about this, that's in fact the architecture. Okay? How you interpret DAGs is the architecture. Pure minimalistic in meaningless sense. The blue is principal-specific types. And you could in fact imagine that eventually people will say, HIDs, how old-fashioned? We don't want those anymore. Okay? And that IETF will decide that will obsolete. Okay? And so over time, what blue boxes are supported or will change. Also, there is no requirement that every network will support all types. So for example, I imagine that your optical backbone at the tier 1 or level, I don't think it's going to run services. Okay? So it would just do ADs. It would not support hosts, it would not support services, it would not support content, straight AD based forwarding, assuming you can get to it. Okay? So the point is there's a lot of different networks in the different things. But that's basically what our processing pipeline is. Okay? We have an evaluation which I'm going to skip over, which basically shows that you can forward this at pretty much the same rate as IP. Okay? If you do a CPU server implementation. This uses the packet shader.
What do you
The variables are packet size on the x-axis and the performance in gigabits per second on the y-axis. The only penalty you pay is effectively that your address go high. So fewer useful bits go through, right? That's what they do that, right?
But we use custom hardware for all.
But in the end, you're going to have custom hardware, and this doesn't matter. But the first time we submitted this paper, it was rejected in part because people didn't seem to like the fact that we have a performance evaluation. So the students went off. So the other thing I want to point out is that there's a number of performance optimizations that you can do, which I actually apparently threw out, which do things like caching of lookup results, right, and so on. And all these work here as well. And then finally,
do you look at, I mean, you obviously have data from what you do. And from the data, you can determine, like we used to do in the old file allocation problem, demands for certain things. Do you redistribute the content to make the time better or anything like that?
can we talk about this again? Sure. Okay, I just want to get through this and then we'll have a more discussion. The next thing I want to talk is about our prototype, which I'm actually kind of proud of, even though I didn't do the writing of it. But, so it's kind of a funny story, and I hope, given that there are a lot of students in class, in the room here, I hope there's something you can learn from this. This is XIP, right? This is IP replacement that we built. It turns out we had a full prototype of XIP running within 6 months of the start of the project. Okay? And we felt really good about this because we had an XIA network. Well, not so fast. It turns out if we try to give this to a user, they say, what? What do you want me to do with this? So it's pretty clear that we needed something called sockets, or something that an application can use to send packets. So we ended up defining a socket API, which turns out, as is suggested here, has actually a number of elements which I'll get to later. Then you discover that when you start doing experiments, any packet loss means your application hangs, unless your application has transport support built in. So we figured out very quickly we needed at least some minimal transport protocols to just be able to write meaningful applications. It turns out that our transport protocols right now, I think the graduate students will hate it if I say this, but they're at the level of a senior level undergraduate project. They're enough to keep us going along and to keep us moving. And there's research going on transport protocols that eventually will be inserted, but for now, this is just placeholders. And so specifically, we have something that is an expressive version of UDP, an expressive version of the TCP streaming protocol, except it's not TCP. And that this supports the content identifier of fetching of data. It's a chunking protocol. So once we had this, we thought we were done. Anybody see anything that's missing here? You're an application developer. What's missing here? Actually, there's a lot missing. I only have half the boxes that I need. So, what?
Well, no service lookups and all that.
Well, naming.
Yeah.
Naming would be good. Also, the moment you try to bootstrap a network, you're going to discover you need things like DHCP, you need Rally, you need ARP. So we then went off and we basically did all this stuff. We had a porting line, we added some basic routing, we ended up ARP, we have actually an ICMP version which is XCMP, and we have an XIA. And now I really think we're done, at least for the first version of it. So right now this is actually all running. We hope to release this within the next couple of weeks. And so if there's anybody here who's just dying to write some weird application for a weird network architecture that nobody outside of CMU, Boston University, and Wisconsin uses, we'll happily ship you the code, actually.
So, I'm not sure what gain you would get, but have you thought about just getting some leased fiber and making this an in-between university protocol?
Well, actually, no, we're not going to lease fiber. I've been in that business and I hate it. So right now we're actually mostly looking at Genie in terms of providing the experimental infrastructure. So we're running our experiments over Genie. We have two modes actually. One is within virtual machines, and the other one is to run on Genie. And the release will actually be specifically tailored to support Genie use and support virtual machine type of experiments. You don't want to lease fiber. So anyway, our prototype is based on Plague. which actually I've always respected Click, and I still do. So I'm okay with that. The initial release, I really got my slides mixed up here. Obviously, this didn't happen at the end of January. At the end of January, we had everything except for the yellow stuff. Then we hadn't had the yellow stuff. Focus is basically on gene-based experiments, and a lot of the boxes, the blue especially, and to some degree the yellow boxes are placeholders. So let me end almost on a somewhat funny note. I was actually talking last week to a student who was admitted to our PhD program and who was visiting, and I was talking about XIA. And I showed this student this picture because I was very proud of this, and I had turned out I had a copy on my desk because of the meeting. And the student looked at this and looked at me, and she said, she was a bit worried, and she said, "Boy, it looks like you're all done." And so the answer, of course, is that we're not. So this is actually my newest attempt at animation in PowerPoint. So it turns out that we're kind of done with the first version of this, right? And now our research is, how can we make everything else in the network better? How can we build better transport protocols? How can we build better routing protocols? How can we make users more confident about the network? And so now what we're really doing is we're kind of just building on the XIA core on really this narrow waist. And now the research is looking at congestion control, how do you deploy services, what does it mean to have intrinsic security if you have services in the middle I have some students did a lot of work in supporting mobile users, for example, effectively, so we're porting that to XIA. So in a way, you can argue the research just started. And in fact, we're really kind of having a little bit of a challenge here in finding a focus, because we obviously can't do everything. We need to find a focus. And then some ongoing research activity. I just want to identify a couple of things because they came up in questions. There was the question that keeps coming up, why packet-based? Why packet-based? So actually, to be honest, if you look at the industry today, it doesn't really use traditional packet switching anymore. A lot of the carrying is over MPLS, right, which is still packets, but it's virtual circuits. So Adrian Perrick, who's also part of this project, has this new path selection protocol called XIA, which is effectively, has a little bit of an MPLS flavor. Again, it should be if I put it like that, but the idea is that rather than having a fully distributed path selection like in BGP, we're effectively building paths as consisting of an uphill path and a downhill path, right? And so the one end of the connection picks the uphill path, the other part of the connection picks the downhill path or potential downhill paths, and then you kind of combine them, right? And if they cross, then that's good. If they're peering links, you detect them. And so it turns out that what you effectively get is you end up identifying paths, and your packets carry a path, right? Now the path, the hops in the path are actually short cryptographic identifiers, and they're a lot like MPLS tags. If you look at the way they are, if you look at the way they're being used, and so it turns out that he's actually, well, the students are working on a prototype in parallel with us, and then we actually plan to combine these two when we get to the, once we're both ready with our first version. The thing is that there is actually a fairly simple way of embedding his paths in our DAGs, right? And so we're basically going to explore that. And for me, this is actually very interesting because we can basically, on top of XIA, explore kind of a BGP-style routing strategy and more of a path-based routing strategy, and kind of look at what are the issues, implications for business.
So do you connect that all with NetFlow and anything like that?
I don't think this will run over NetFlow. OpenFlow, you mean? OpenFlow. So the problem is OpenFlow is pretty IP specific.
You can change it.
But you can't change. So our preliminary evaluation shows that they just don't give you access to enough bits in the packet. They're focused on.
The only reason I'm asking is because the industry likes that.
I understand the industry likes OpenFlow. I'm kind of no longer particularly interested in the performance question, unless you can go off and we don't, like if somebody wants to do this on an FPGA and really kind of try to be clever, I'd be interested in it.
We're working on a new project in Europe where we're doing actually heterogeneous traffic OpenFlow, try to accommodate wireless and everything.
Okay. Well, so I'm not saying nobody should do that. This is not on our. This is not the top 10 thing for us.
Because that essentially goes towards circuits and Flow is a another thing, not bucket.
Yes, no, I think that's right. Some of the fast applications maybe also go in that direction.
Okay.
So anyway, this is kind of what I have. So I'm sorry I went long because of something, but and I didn't address all your questions, but hopefully there's enough now that we can talk about some of the questions.
Thank you. We have time for a few questions.
I just want to, so at least during the first part of your talk, you were talking about the user. So sometimes, what type of user do you imagine? Like my mom is a user for this network? Because if my mom is a user for this network, then this approach will fail.
Does your mom have a PhD in computer science or not?
No.
Just tell us something about your mom.
So actually, there are. Let me give you a short answer, but there's a couple of pieces to it. Right? The first thing is that when I use the word user, I've been very informal.
Okay.
So because, and in fact, I get yelled at if I think this that's to you. The reason is that depending on how you look at it, the user is either a human being, or it's an application, or it's a network manager operating your edge network.
But
And so I'm going to get to your mom, okay?
Okay.
So the thing that's interesting is that if you look at which of these users you mean, it really depends which question you're looking at, right? If you're looking at trust in the network, obviously you're talking about a human being. If you're talking about being able to control what type of XID you're using, right? Whether it's a content identifier, service identifier, it turns out today, chances are your application has something to do with it. Okay, so certain aspects of security, you're really forced to do whatever your application does or doesn't do. And also a lot of decisions on this are really ultimately that your network manager, like CMU, will not allow certain types of traffic or whatever, right? So we need to be a little bit careful here. Now, obviously from the context, it's clear that you meant people, right? So obviously the user we mean is your mom and my mom. Okay. Obviously, we're going to need stuff between what I discussed and between where your mom sits, right? And that's really boils down to two things. The first one is, what does really the interface between the application and the network looks like, and what's the degree of control you have over some of these trade-offs that I mentioned? And then the other one is, how is this presented to the user, right? So to give you an example of a type of project that we're working on right now, I have one of my students in computer science working with a student in HCI and with a faculty member in HCI. And we're kind of saying, look, suppose you want to provide the user with an interface that gives them some idea on things like how much information they're leaking to the network, given what the type of traffic that their application sends. Okay? What would that interface look like? If you would then eventually for XIA add control to it, what would be the controls that you provide? Right? So for example, the current interface that they prototype is going to show what type of XID types are being used. Right? So if you see a lot of content identifiers, you see that you might be worried. Right? Obviously, right now this is really targeting people who know what they're doing. Right? There's a whole separate question of how you educate people about this. Another thing that actually the HCI people are interested in, they kind of want to know which ISPs are involved in forwarding the packets. And this is in part because of some, not so much a concern for US users, but for users in other countries. And so the idea is to kind of start to look at giving this information on a routine basis to users, potentially. In the current internet, it turns out users have zero control over this, so you can't provide controls. But eventually for XIA, we could provide controls. And what would these controls be? Right? So no, we haven't answered this question, but we are aware of it, and we're kind of starting to take baby steps towards addressing this. But it's a very good question.
Yeah, question.
Yeah.
So the security, extreme security that you mentioned, I think they provide integrity and authentications. So how do you provide confidentiality? So like if I want to request a piece of content, for example, but I don't want you to know that I'm doing it, or like how do you?
Well, yeah. So I mean, I think a lot of the ways you would do that are similar to what you would do today, right? I mean, if you want confidentiality of content, presumably you will encrypt it. So I'm not sure where you, so I'm not sure, it turns out that a lot of the solutions for the internet actually works just fine. One of the things that we need to spend more time on, and is on our list of things to do, is to see to what degree things like intrinsic security can simplify some of this. There is, for me, actually, and there may be somebody in the room here who's actually very well qualified to look at this, there is kind of this very interesting trade-off that you really face, because you can in fact get, at least on the surface it looks like you use content identifiers and still have privacy if you encrypt the content. Okay? The thing that's interesting though is that if you have one person, one client who knows the key to decrypt the content, then you get very strong privacy. You can still use content identifiers, but you lose all the benefits that come with it because you can't do caching is not useful, right? And so there's this kind of really interesting question of, can we really quantify kind of this trade-off here between some of the privacy properties that you get and between some of the efficiency properties, because this really does seem to be a very fundamental trade-off, right? And so I think, yeah, we can do pretty much everything you have, and over time you're going to need to look at how you can potentially do better by using some of the mechanisms we have in XIA. But as I said, we haven't really gone too much with that at all.
Any other questions?
So do you tackle those big problems we have now, like annual meeting, somebody sits there and do some bad things and nobody knows who is it and where he's sitting? And do you tackle those kind of problems here?
Well, yeah, this is a little bit vague.
Can you invert the DAG?
Can I what?
Invert the DAG?
I can invert the DAG.
You can find who is it.
Well, I mean, so can you identify who sent the packet? Is that it?
Yeah.
Well, actually, we use the source DAG for that, right? Inverting the DAG is not really helpful, and whether the source DAG is correct is a different question. But presumably, any router can identify whether the source address is legitimate, right? So potentially, right? Do that. One of the things I do, your question is vague enough that I think I can give an answer that is probably not helpful. But I actually kind of that at least may clarify some things. One of the things that we've learned in working with users, with the human variety of users, is that they really don't get it. This whole internet and security thing.
They don't get it.
They don't get it.
They is.
It being what security is and what privacy is. And what these things are. So one of the things that we, for example, one of the students working with the HCI faculty member interviewed a bunch of random users and asked them about their privacy concerns in using the internet. The fact of the matter is they cannot tell the difference between privacy issues raised by having a specific, let's say, identifier in Facebook and between having a package travel through an ISP. They cannot tell the difference. For them, this is just like, huh? This is different? I have control over one and not over the other? I mean, so they really don't get it, right? And so, specifically, we are really focusing on the network. We are not really worrying about how Google or Facebook or whatever your favorite social networking site is deals with privacy issues. It's not that it's not important, it's just that it's pretty far removed from the network architecture, right? We are concerned about any privacy issues raised at the network level, but the other thing is really explicit outside of scope for the project.
Just to maybe press, I think that you have answered part of my question, that let's say you receive spams and you don't know where it was sent from. Those kind of problems we have in the internet. How do you deal with? And just following this question, I mean, you were talking about users. This is my idea. I think that all those things that you were mentioning about my mom, my grandma, should be transparent to the users because they don't get it. So,
I understand this, but actually what I want to emphasize here is that we can't solve all ills in the world. Right? So we're focusing on the network. Okay? So a lot of these issues, are really application layer issues, and these are valid. They're legitimate. There are lots of people working on them, but they're not part of our project.
You want to ask the question again?
No. So this is like a philosophical thing. So it seems like to me actually what this is moving away from internetworking. So the IP protocol was like really concerned about internet. How do we connect networks? And now we're sort of abstracted to a higher level, sort of like content-centric networking is doing, where it's not about how do we connect networks, it's just how do we get data. It doesn't matter where the heck it comes from, right? You're shaking.
Finish your question. I don't want to disagree with you before you finish.
Well, so I guess I'm curious, and then when you showed this diagram of, oh, we have to deal with DHCP and all these things, then it became clear that internetworking is still an incredibly important problem that has to be dealt with. But at the same time, the ideal is no more internetworking. At least that's what the XIP ideal seems to be, at least in here.
Well, actually, it turns out that the way we present XIA changes over time. And so whether you would look at this as focus on internet networking or not, probably changes over time. But I would actually largely disagree with this statement. Fundamentally, IP is meant to be an interface between networks. I mean, you know that obviously. And so it happens to be that for probably mostly for economic reasons, people are also using it inside networks, right? Because the hardware is there and it gives you the right management features and so on. However, you know, that trend has kind of changed because now a lot of people are using MPLS inside their networks, right? At least ISPs, not edges. The thing that's very interesting, I mentioned Adrian's work on SIGN before. It turns out that SIGN is really, it's an inter-networking protocol or path selection protocol, but you cannot use it in any kind of meaningful way within an autonomous domain. So it's really meant to be really purely a BGP alternative, right? So we really look at this as being an interface between networks. The thing that I think is really kind of an interesting issue, though, is that at least our current view is that, to get back to your earlier question on routing, right, we really envision that the protocols that are used for routing content and services are going to be very, very different from those used for autonomous domains and hosts. And so, and the reason is simply that the business models are different, right? And so, so for example, I have a content cache, you have a content cache, okay? Well, there's a business arrangement to be made here in terms of whether we want to share the indexes for our caches, right? And it's going to really depend on our relative position in the ISP hierarchy. Yeah, you know, where you are, right? Because it turns out that, you know, there's been some research done on the incentives for deploying caches. And, you know, it turns out for certain providers, it's just completely silly. It hurts their revenue if they deploy cache, right? Because they can't bill their customers more traffic.
Or they don't have enough to need caching.
Or they don't have enough to need caching, maybe the nature of the customers, and so all these types of things. And so same thing for services. Some service forwarding will be for internal use, but you know, I think things like the big websites may want to make business arrangements with different ISPs to basically have their service identifiers explicitly routed by their ISPs. But it's not going to be BGP. Right? It's going to be a very different protocol, and it reflects the business model.
That's right.
Okay, let's thank Professor Steenkiste. So we will have a roundtable